Let's take a look at section 7.6 where we're looking at complex numbers. The set of complex number arises from the fact that we define an imaginary unit called I as being equal to the square root of -1. Because of all that we've said about radicals, if I is the square root of -1, then I squared has to equal -1. So, because of this single definition of the imaginary unit I, an entire set of numbers arises called the complex numbers that contain and are bigger than the set of real numbers. So, every complex number can be written in the form a plus bi, where the conjugate of a plus bi is a minus bi. And the product of a complex number with its conjugate is, and you can see why this is true by looking at these three steps here, a squared plus b squared. So we want to use this information to write negative square root -75 plus square root of 16 in the form a plus bi. So I'm going to break this into three radicals. The first radical is going to be the largest perfect square factor of 75, and that's 25. The last radical is going to have 3 because 25 times 3 is 75. And then the middle radical is going to have -1. So this is how I'm going to simplify negative square root -75. And then the square root of 16 is 4. So this is minus 5i square root 3 plus 4. And that's my final answer on that one. That would be this. Well, let's actually get it in the right form where we have the real part first, the 4. It's called the real part of the complex number. And then the minus 5i times the square root of 3 comes in second position, and minus 5 square root of 3 is the imaginary part of this complex number. Okay, so that is our final answer on that one. Okay, here we want to write the quotient 2 plus 3i over 5i in the form a plus bi. So what we're going to do with this is we're going to multiply numerator and denominator by the conjugate of the denominator, which is minus 5i. And we're really just multiplying by 1, so we're not going to change the value of this expression. So 2 times -5i is -10i. Positive 3 times -5i is -15i squared. And then 5i times minus 5i is positive 25i squared. And we're going to replace the I squareds with -1, since I squared equals -1. So in place of the I squareds, we're going to put a -1. And I get -15 times -1 is 15. And I have a subtraction of 10i. 25 times -1 is -25. 25 times negative 1 again is negative 25. So 5 divides into 15 3 times, and into negative 25 a negative 5 times. And then we have a double negative here, so that becomes a positive. Minus 10i over negative 25 becomes positive 10i over negative 25. And again, we can divide the numerator and denominator by 5. So we get 2 over 5i. And we've accomplished our task of writing this in the form a plus bi. Okay, here we have a product of conjugates. And we saw on the first page that a minus bi times a plus bi always equals a plus b squared, a squared plus b squared. Now that's always what happens, and you can use this result to save time. But suppose I didn't know that or didn't believe it. Then I'm filling into this template a squared minus b squared. But a in this case, so the real part is my a of the complex number, that's 2. And the imaginary part is the coefficient of I, and notice that's the square root of 3. So this is 4i, square root of 3i. This is 4 minus square root of 3 squared is just 3. And then I have to square the I squared. So 4 minus 3 times negative 1 is a positive 7. So this turns into 4 plus 3. Okay, because I squared is negative 1, we should never have I to a power greater than 1. So I to the 31st is written as I to the 30th times I. So we basically want to have, we want to use the fact that we know what I squared is in order to simplify this. So I to the 30th is I squared to the 15th. And this is all going to get multiplied by I squared is negative 1. So that's what we're raising to the 15th. 15th power applied to negative 1 gives me negative 1, which gets multiplied times I. So I wind up with negative I as my final answer on this one. So now we want to write 2 plus I over 5 minus 6i in the form a plus bi. And we're going to do that. Here's one of the special uses of the conjugate. We're going to do that by multiplying the numerator and denominator by the conjugate of the denominator, which is 5 plus 6i. So I change the sign of the imaginary part to get the conjugate. And so 2 has got to get multiplied by 5 plus 6i. And so does a positive I. Then in the denominator, as we've seen, whenever you multiply conjugates, you're going to get a squared, which in this case is 5, plus b squared, which in this case is the square of 6. B is 6. All right, so I'm going to expand this, and I get 10 plus 12i plus 5i plus 6i squared is divided by 25 plus 36, and 12i plus 5i is 17i, and I squared is negative 1, so we're going to be multiplying 6 by negative 1. Alright, and positive 6 times negative 1 is negative 6, so this becomes 4 over 61 plus 17 over 61i. That's our final answer. Then, of course, you can multiply, you can find the product of complex numbers. In this case, 3i is being multiplied by 2 minus 5i. So 3i gets multiplied by 2, and I subtract from that 3i times 5i. So 6i minus 15i squared. And that's equal to 6i minus 15 times a negative 1, because I squared equals negative 1. So negative 1 times negative 15 is 15 plus 6i. That's my final answer. And we can add and subtract complex numbers. And when doing so, we kind of treat I like we would any variable term. 4 plus 2i minus 3 minus 6i. So I not only subtract the 3, but I also need to subtract negative 6i, which is positive 6i. So 4 minus 3 is 1. 2i plus 6i is plus 8i. And that's my final answer. Okay, here's a product of complex numbers where we need to use the distributive property twice. So we have 5 times 1 plus I minus 2i times 1 plus I. So 5 plus 5i minus 2i minus 2i squared. So those are the 4 products I get. And 5i minus 2i is plus 3i. And negative 2 times I squared is negative 2 times negative 1. So I get 5 plus 3i plus 2. So in the form a plus bi, I get 7 plus 3i. All right, when I go to multiply complex numbers that are in the form that I see here, square root of negative 25 times square root of negative 4, I first have to simplify them. I can't actually use the product rule for radicals here because these radicals do not represent real numbers. So I have to take the square root of negative 25. I'm going to write it as the square root of 25 times the square root of negative 1. And then that gets multiplied by the square root of 4 times the square root of negative 1. Square root of 25 is 5. Square root of negative 1 is I. So I have 5i times square root of 4 is 2. Square root of negative 1 is I. So 5i times 2i, which is 10i squared, which is 10 times negative 1, which is negative 10. So that's my final answer. So notice if I had multiplied the radicands and put them in one radical, I would have the square root of 100, which is 10. But the product rule says I can only do that if both radicals represent real numbers. Now here I have the square of a complex number 4 minus 3i. And the template for squaring two terms that are either being added together or subtracted is that you get the square of the first term. In the case of subtraction, minus 2 times the first term times the second plus the square of the second term. And in our case, the first term is 4. And then 3i, if I'm thinking of this as the square of a minus b, a is 4 and b is 3i. So this is 16 minus 8 times 3i, which is 24i, plus the square of 3i, which is 9i squared. And then remember that I squared is negative 1. So this becomes 16 minus 24i minus 9. 16 minus 9 is 7. So this is 7 minus 24i. And that's my final answer. All right, and this is the worksheet for section 7.6.